All right, we're now going to do part 2 of our lecture today on this Cesar Chavez Day, I believe. Fresno State has the day off. We do not. Learning does not sleep or something. I don't know. So we're going to do a little bit of review. So over the break, I read everyone's essays on where they're at and what they want to learn more on. And a lot of students said I want more information about pointers and memory and that kind of stuff. Big O as well. So, and the Starship operator, which I kind of just went over in the previous lecture. That will automatically generate a function that will compare points. It generates a less than operator for you, a greater than operator, a double equals operator. And it sorts first on X, then on Y if there's a tie on X. Okay, well, there you go. Learning point 3 done. All right. Now let's do memory allocation. So let's talk about memory allocation. So there are two main places where data is held, arguably 3. There's the data segment where constants are held. The constants are oftentimes sort of optimized away and don't appear in your code at all. So there's really kind of 2 main areas you need to worry about, with a third that we'll maybe talk about later. First is called the stack. Second is called the heap. Okay. Stack is, on the order of 5, 10 megabytes big. If you exceed this, you die. Okay. Now, an easy way of overflowing the stack, if you've ever been to stackoverflow.com, is for a function, a recursive function especially, to recurse too deeply. It dug too deep, like in the mines of Moria, and then you'll run out of stack space. Because the way that the stack works is every stack allocated variable, automatic variable, that's where the auto keyword comes from. It actually meant stack allocated, but everything's stack allocated if you don't specify auto, so nobody used the auto keyword, but it was still reserved, so that's why auto became auto. So every regular variable is stack allocated, including arrays. Okay. Heap is big. It's on the order of 2 gigs on or something like that. These are configurable parameters. I'm just kind of tossing out ballpark numbers. You can change them on your own system and things like that. But, just kind of get an idea. The stack's small and the heap is big. Okay. And if you knew something and you're out of memory, it's actually kind of hard to run out of memory these days, so I don't know if I want to talk about it. But new can return a null pointer, and you can check for that instead of just dying. Or it can throw, but I mean, we almost never run out of memory these days. So, probably should talk about it. But basically, only new things are heap allocated. Okay. So if we have integer array equals new int 100. Everybody tell me, is this stack allocated or heap allocated? Where the pointer itself is on the stack, but we're making 100 integers, which is 400 bytes. Is that memory coming off of the stack, or is that memory coming off of the heap? Give me an answer in chat now. That's terrible. Too detailed, not detailed enough. Yeah, this won't work. Sure. Okay. So we got 2 votes for the heap, 1 vote for the stack. There's 11 people on stream right now. Come on, I want to hear this from everybody. Managed automatically by the compiler. Managed by the programmer. Yeah, the programmer calls new. Regular variables automatically get the memory allocated for them. When the function goes out of scope, all those variables automatically get deleted. sort of automatically. Anybody else? Noah, Goosey, Santiago, Wallace. Are those 400 bytes of memory coming off of the stack or off of the heap? They're coming off the heap. Okay. So this is a heap allocation. And this memory sticks around until we do a delete. So we need to do a delete at some point to free the memory back to the heap. Okay. If we don't do that, then we will get yelled at by this equals address. We'll get yelled at by address sanitizer. Unused variable. Yeah, I know. Leak sanitizer detected a memory leak. We allocated memory. We did not deallocate the memory. This is why it says managed by the programmer. You are responsible for freeing the memory, but you own that memory as long as you want. Stack allocated memory goes away when the function ends. Discord went down again, and we're back. Okay. What about this guy? Integer x. Is stack or heap allocated? Everybody on chat, give me your answers. Integers are 4 bytes. So this is going to allocate 4 bytes of memory off of the stack. Very good, everyone. And so x goes away here. X gets deleted here. Okay, so the way it works is you've got a stack pointer. Every time the function calls another function, the stack pointer moves down to allocate enough memory for all the different local variables within that function. And when the function returns, the stack pointer goes back up, and all those things get deleted. They've got destructors. It calls destructors on them. Now, that's great, right up until the fact you do a recursive call. So let's call this getRect for recursive, right? Integer x. And we'll say if x is less than or equal to 0, return. Integer array. How many bytes is this? And is this stack or heap? So while you guys are answering that, we will recursively call down one more time. So basically, if we pass in getRect with 1, it's going to call this function once. It's going to allocate some memory off the stack. Very good, 4K off the stack. And then it's going to call itself again, which will again allocate 4K off the stack, even though even though the function's not really doing anything. It'll still probably allocate another 4K. And then it returns. And then it's going to free up both those 8Ks. So we can have some fun figuring out, yeah, that is definitely stack allocated. And this is definitely 4 kilobytes of RAM off the stack. We did not call new. New is how you get heap allocated memory. Yep. That's the only way you get heap allocated memory. And so you've got a very small budget for stack allocated variables, right? So making large arrays in a recursive function is a great way of segfaulting, as I'm about to show you. Okay. So let's go ahead and get it wrecked. If I pass in 1,000, how much memory is this going to allocate? It's going to call itself, and it's going to call itself, and it's going to call itself 1,000 times. Each time it calls, the stack pointer moves down 4K plus a little bit of change. There's a little bit of overhead in a function call. It's got a 16 or 24 bytes of overhead, something like that. Not a lot, but still enough that you don't want to recursively call yourself like hundreds of thousands of times. So how much RAM is this going to take, guys? And is it going to segfault? Yeah, good question. C-style arrays like this are always stack allocated. It makes them dangerous. The benefit of them is that they're fast, right? The C-style arrays are really bad. Like in general, my advice to new programmers is just to not ever use them. Because there's a lot of bad things going on here. One, we're probably going to segfault, or we're getting close to the order of where we're going to segfault. I don't know exactly. We'll find out. But also, it's uninitialized. Like we didn't. None of this RAM is initialized. You've got these arrays filled with uninitialized integers. It's very fast because it doesn't have to initialize all the memory. It just moves the stack pointer down. When it's done, it moves the stack pointer back up. That's it. It doesn't have to do, order and work initializing all the stuff. Arrays are fast, but my advice to new programmers is to use vectors instead of arrays. Vectors are heap allocated. The vectors under the hood, as you guys should know from your vector group project, is that a vector news memory, and then when it fills up, it doubles. Sometimes it depends on the implementation. Some do like multiply by 1.5, but let's just say double for short. So it doubles the size of the memory, copies the stuff over, unallocates the old one. And so it's doing the news and deletes for you, but it's still heap allocated. So vectors can be very big because they come off the heap. Whereas arrays, C-style arrays like this, come off the stack 100% of the time. Okay, so Olson has done the math. It is going to do about 4 megabytes of allocations, no segfault. Okay. Let's multiply it by 10. Segfault. Okay. So 40 megs is too much. So right now this is allocating 40 megabytes of stack space. We're getting a crash. 4 megs was okay. Anyone want to guess somewhere between 1,000 and 10,000? I'll give you a point of extra credit. Whoever is closest to the number, it's between 1,000 and 10,000, as we've seen. Let me just double check that 1,000 one segfault. Okay, good. So pick a number between 1,000 and 10,000. Pick any number you want. Whoever's closest, I'm going to give them an extra point. All right. Enter your votes now. All right. So the votes are in. Let's start with the biggest number. Goosey with 8765. 8765. And that's a segfault. So, nope. Let's go to Gunnar Lamar. 7777. Segfault. All right. Let's try Luke Olson's 5000. Segfault. Let's do some binary search. 2500. Segfault. All right. 1200's okay. Let's try 2000. 2000's okay. 2250. Segfault. All right. Homing in on things. Segfault. So let's see. Kevin Viale looks like our winner. Very nice. Very nice. Very nice. Literally the lowest guess. Everybody else was far more optimistic about how much RAM that we have there. So yeah, so it's not like this is a hard limit. Like they're limit. So the stack is hard limited to 8 megs on this. I don't want to say on the system because I can change it, right? I could say limit stack size to more. Like you can adjust the size of the stack. The reason why it's kept small is so that if your code goes out of control and starts recursively recursing out of control, then it'll hit the hard limit sooner and die. So that your code, you don't just sit there like, what's going on? It'll die, right? Instead of just looping. Like if you up the limit to like a gig, like that thing could be going for a long time, recursing until it hits the limit. So you can set stack to whatever you want. If any of you guys have ever played Minecraft, like you probably know that there's like a stack. Let's see if I'm remembering this right. Java Sir. believe that's increasing the stack size of the Java server in Minecraft. And I think one's like for stack size, one's for heap size, something like that. I don't know. I haven't looked at it in a while. Okie doke. So, let's ask some more questions. How much memory does a pointer take up? We have a pointer. How much RAM does that take up? How much does the regular variable take up? Point P. How many bytes of RAM? So, on a 64-bit memory system, how many bits is a pointer? All pointers are the same size, by the way. It doesn't matter how big a thing that you're pointing to. It's one of the benefits of using pointers, is that all pointers are the same size. And so there's some really interesting tricks you can do where you can have a pointer to something, but you don't know what that something is, but it's okay. You can have an array of these pointers because all the pointers are the same size. So we know how big it's going to be, even if we don't know exactly what they're pointing at. There's some really interesting tricks that you can pull with pointers that derive from the fact that all pointers are the same size. On a 64-bit system, they're all 64 bits, which is 8 bytes. And yes, Wallace, you're correct. They are 4 bytes on a 32-bit system. That's why 32-bit systems run out of RAM. Right? Like if you ever played Fallout New Vegas recently, it's rough. Because Fallout New Vegas is a 32-bit application, and so it can address at max 4 gigs of RAM, and I think it can only maybe even do 2. And so when you install mods that like add all sorts of stuff, it literally runs out of the 2 or 4 gigs RAM, whatever the limit is, I can't remember, and then it barfs and dies. And so it's my hope that with the new Fallout TV series coming out, they're going to redo Fallout New Vegas, which is my favorite RPG of all time. If for no other reason than just to give it 64-bit support. If they just gave it 64-bit support and really maybe just minor improvements to the engine, kind of like they did with Skyrim Special Edition, then modders can handle the rest, trust me. But right now, modding it's really annoying because they're 4-byte pointers. They're 32-bit pointers. A pointer on a 64-bit system. 64-bit system has a 64-bit pointer. All right, which is the same thing as 8 bytes. Okay. There are bits in a byte. Anyone know what a half byte is called? Half byte, which is 4 bits, is called a nibble. Yep. Does 3 have 64-bit support? Fallout 3? I think not, actually. I think Fallout 3 is also 32-bit programming. 3, 64-bit patch. Well, yeah, we can get distracted by that, but they have, like, Bethesda has actually pushed a new development branch of Fallout 3 and Fallout New Vegas to Steam. So I would love to replay Fallout 3 and Fallout New Vegas with 4K graphics, upscaled textures, 64 bits. It's April. Maybe even this month we'll see it. I don't know. Ever since Microsoft bought out both Obsidian and Bethesda, I've just been waiting for them to like either redo Fallout New Vegas or a sequel. Here's hoping. All right, so on a 32-bit system, all pointers are 32 bits. Cool. How big is this guy here? Point. How big is that? We can like see out the size of the pointer. Fallout Anthology, yep. Suspicious usage of pointer to aggregate. No, it worked. Okay. Well, there's the answer, by the way. So, points are 16 bytes because a double precision floating point number is 8 bytes each, and we got 2 of them. So a float is 4 bytes. A double is 8 bytes. And so every point has 2 doubles. Now you might be like, well, what about the operator? Doesn't that take up RAM? Nope. The operator is just a function. Functions aren't actually part of the point. It doesn't take up any RAM. If you make an array of points, it doesn't take up any RAM. It's just a function in the code section. Okay. What about if we added in a Z? A Z, as the Brits say. How many bytes is this going to print here? What do you guys think? So every point now is how many bytes? 24? 24 seems reasonable to me. What about the pointer? Does the pointer get any bigger? Do pointers ever change in size? So remember, a pointer holds a memory address. And so in order to hold a memory address of 64 bits of memory, you only ever need 64 bits. So no, pointers are always the same size. And yeah, so it's up to 24 bits now. Cool, cool. All right. What if we wanted to add an integer here? Integer bar. Okay. Ints are 4 bytes on our system. In most systems these days, they're 4 bytes. They don't have to be. There's no rule that says they have to be 4 bytes. But they usually are. So how many bytes do you think a point will take up now? We'll take up now. What do you think? Can you do math? Is the math going to work correctly? What do you guys think? The double XYZ is 24, and we're adding 4 bytes for the integer. 28. Interesting theory. Interesting theory. It's actually 32. What if we added another integer? Let's add. So we're at 32 bytes right now. We're going to add another integer, 4 bytes. How much RAM do you guys think this is going to take up now? So we were at 32 bytes before. We just added a new integer that's 4 bytes. How many bytes do you guys think it's going to take up now? You guys got it. 32 still. The reason for that is because when you have a double, everything has to be aligned on an 8-byte boundary. So the memory addresses have to be divisible by 8. And so with the integer here, you basically lose 4 bytes because it's a 4-byte thing. And so of the 8 bytes reserved for it, you're only using 4. So when we allocated Sydney just slotted into the unused 4 bytes that we were using before. The 4 bytes of padding, we call it. Okay, so neat. All right, let's have some fun with pointers. Let's just move on to number 4 here. Pointer fun. So we're gonna have point putter, as Arthur Dwyer mispronounce it. We're gonna have point putter and putter 2. Let's actually do this. Let's do this. Let's actually erase everything. Let's just slash and burn the entire thing. We're gonna make a Pokemon class. A Pokemon class is gonna have a name, which should be a string name, and it should have like an integer for like attack and defense and speed, health, and special, blah 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 blah, and types and things like that. Okay, whatever, good enough. So we got this Pokemon structure, right? And we're gonna have a couple Pokemon fighting each other. You know, cage fights between dogs is generally frowned upon in polite society, but when it's a kids show, it's okay. So that's all right. All right, so we're gonna have Pokemon Pikachu. Don't sue me, Nintendo. And we're gonna have Pokemon. Man, Tyke. All right, and we can initialize all these things. We use an equal sign, or we don't need an equal sign. It's all good. This guy's called Pikachu, and his type is lightning, and his attack is 10, 30, 50, whatever. I'm just making up numbers. Okay, and then for Mantike, water type, and it'll have more attack and less defense and more speed and less health. Okay, semicolon there. All right. So let's say we're gonna be going back and forth. We're gonna be writing code where the player will pick a Pokemon, and then they'll pick a move on the Pokemon, and the Pokemon will do the move and deal damage to the other side. And then it's that guy's turn if he survives, and then he shoots water, hydro, thunder, whatever back, and the two trade blows back and forth until one of them dies, right? Your typical, cage fighting for kids, right? The problem with this is that if you're going to be writing this code, you're going to end up copying and pasting the same code, right? Like you're going to have code for Pikachu hitting Mantike, and then you're going to basically copy and paste the whole thing for Mantike hitting Pikachu, right? And there's a principle in computer science called DRY, which stands for don't repeat yourself. Have you guys heard this phrase before? DRY, don't repeat yourself. I'll say it again, don't repeat yourself. So, we don't want to repeat ourselves. And so, how can we do it, though, without just copying and pasting all of the code? Like, you have algebra coming on, like Pikachu dot attack times, move dot attack divided by Mantike dot defense. Like, you got all this algebra, and then you want to switch it around without having to copy and paste all of that combat code. Let me show you a cool thing you do with pointers. Because one of the most common questions I got was like, give me some more uses for pointers other than all this data stuff, the data structure stuff we've been doing. And like the contrived examples are really bad, right? Like, people teach pointers like integer x equals 5, and you have an integer pointer that's equal to the address of x, and then you can say that pointer is equal to 42, and then you can see out value of x, right? And the problem with these examples, which you guys understand this is going to print out 42. The problem with these examples is that like nobody will write code this way, right? Like this is completely pointless code, and the human brain has trouble like retaining information that is pointless, right? And when we tell you that like pointers are not used that much anymore, that gives your brain permission to just like jettison all of the pointer stuff. So let me show you an actual use for pointers. Okay, so we're gonna have a while true loop. While true, in other words, until one of them is dead. Right? And we'll have maybe a Boolean called first player turn, and it's going to be equal to, let's call this like poke1, poke2, right? Because these things are really going to be pulled out of some sort of data structure, right? So first player turn equals, okay, so if poke1.speed is greater than or equal to poke2.speed. Okay. So whoever has the highest speed gets to go first. Easy. Okay. Then we're going to do all this code. Let's do some computations. Let's do integer math, whatever. Integer math sucks. Okay, wait. Maybe don't, whatever. Integer damage is equal to poke1, but I don't want to use poke1. So let me show you something. Okay. I'm going to make a pointer. I'm going to make a Pokemon pointer. Do you see why I don't want to write down poke1 dot attack? Because I'm going to have to take all of that and copy it and paste it for Mantike hitting Pikachu. Do you guys understand me? Like, what I was about to do is say the amount of damage you take is equal to the Pokemon1 dot attack divided by Pokemon2 dot defense. We'll probably cast this to double so that we don't get rounding errors to 0. The defense is higher. times the move dot attack, blah, 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 blah. Something like that. But then I'm going to have to copy and paste all this code after, you know, they survive, and change all the 1s to 2s and change all the 2s to 1s. And I've repeated myself, which, again, I will repeat myself. You don't want to repeat yourself, right? So let me show you a cool trick that doctors hate. I can make a Pokemon pointer called pointer1. And I can make a Pokemon pointer called pointer2. If I want, I can even put them on the same line. Okay. So you can say if it's the first player turn, first, come on, tell us, there we go. If it's the first player one, then in fact, instead of pointer one and pointer two, I can call this attacker and defender. Okay, so if it's the first player turn, and you know, if we want to be safe, we can like set them to null, whatever. Null pointer, 0, whatever. Okay, so if it's first player turns, then the attacker is Pokemon 1. And the defender is Pokemon 2. And if it's not the first player's turn, well, guess what? If it's player 2's turn, then the attacker is player 2 and the defender is player 1. Check it out. Kind of cool. You can do this, and then after the end of the turn, we can say first player turn is equal to the opposite of first player turn. Look at that. Ain't that cool? This works for any two-player game, right? If you got chess, checkers, things like that, at the end of the person's turn, then you go, well, it's now the second player's turn. You know, if first player turn is false, it means second player's turn. Then when they go, it becomes true again. So it flip-flops back and forth between true and false after every person goes. Neat. And what we're doing here with these pointers is that we're having attacker point at Poke 1 and defender point at Poke 2. And then on the next turn, the attacker points at Poke 2 and the defender points at Poke 1. And then it goes back, and then it goes back, then it goes back, then it goes back. And you don't have to sit there copying these values into new variables and things like that. You just have pointers that are pointing at the two, and they just point either like this or like this, back and forth every turn. And then, instead of using poke1.attack and poke2.defense, etc., you're going to say the attacker's attack divided by the defender's defense times 20. See out attacker points to name, damages, defender points to name, for damage. And we can say defender points to health, minus equals damage, so the defender takes damage. And if don't like that, transfer point number into an integer double to int. I know, whatever. Let's use a double. Okay. Now it's still gonna get mad at us. Fine, whatever. Okay, everything's fine. It was just warning about the casting from a double to an int. So, and then if defender points to health is less than or equal to 0, you say cout. Defender points to name. Thanks. And we end the infinite loop. And if the defender survives, then the defender gets a hit back, and then if the attacker survives, back, and they sit there and trade punches until out health renaming. Okay. So we'll sit there and trade punches back and forth until one of them dies. We can make it a little bit more dramatic by adding in a little bit of U sleep to it. Micro sleep is what students do in my class. So microseconds are a millionth of a second. So the U in SI notation is microsecond. So a micro sleep sleeps for 500,000 millionths of a second, which is half a second. So basically, Pikachu is going to punch Mantyke in the face. Actually, Mantyke, I think, is going to go first because it has a higher speed. So Mantyke's going to punch Pikachu. Pikachu takes damage. If he survives, then attack comes back, and there's going to be a little half-second pause in between each one of them. I'll give them a little more health. So the fight will be dragged out a little bit more. Okay. We're doing 40 damage. Let's see if we can make that a little more interesting. Pikachu will have 20 attack and 10 defense. And Mantyke will have 10 attack and 5 defense. Mantyke should get owned now. Okay. You guys see that? And so rather than me having to go through this whole rigmarole for Pokemon 1 hitting Pokemon 2, copy-paste Pokemon 2 hitting Pokemon 1, instead, by just using pointers, I could change who attacker is and who defender is every time and just switch them up, and then I can reuse the same code. What do you guys think? You guys like that? Rerun the battle with Mantyke having a 50 defense now. Give Mantyke a little support here. Pikachu's hitting for 8. Mantyke is hitting for 20. Pikachu goes down. Down goes Frazier. Alright. Yeah. So that's the kind of thing you do with pointers. And that's one of the things that I want you to walk away from data structures with, is this kind of understanding of pointers. And, you know, I didn't new anything here. None of this code here has any news, any deletes, none. Because I generally try not to write code that has a new or delete in it these days, right? I use a vector to do my memory management for me. I don't usually use new or delete at all. But there's nothing wrong with a pointer. Like just having a pointer point at something, that's fine. It's not owning memory. I'm not responsible for deleting it. It just points at something. And then you just change the thing that it points at. And so you point at you, and you point at you, and you point at you. And it's just real easy. You know, real simple. So just pointing at things is fine. It's the thing that makes pointers like really irritating to deal with from an experienced programmer's perspective is knowing when you're supposed to free them, knowing when you're supposed to delete them. And it's almost an unsolvable problem. That's why we have a lot of tricks like RAI and smart pointers and things like that to actually figure out when we're done with memory so that we can safely delete it. It's not a trivial problem. Okay, that is pointer tricks, pointer fun. Yeah. Now we'll finish off with a talk of Big O. You guys got any questions on this? All right, then we will move on to Big O.